want to talk a little bit how perhaps we can constrain it from the stellar side of things. So kind of the one slide summary, if you take nothing else from this talk, is that merging binary black holes can be used to constrain nuclear reaction rates, but only if we understand their stellar progenitors, what stars made these black holes. We've had quite a few good talks this week already about the merging neutron stars, kilonovae, where you get a light curve, which gives you something about the R process, or you get tidal effects and gravitational wave signal to get the equation of state. Unfortunately for the black holes, we get none of that. All we have really is the masses and the spins of the black holes. So what's shown here is just from the LIGO 01, 02 data, so the first 10 detections, is basically the mass distribution of black holes with some set of fits to the population. So what we want to try and do, of course, is to try and understand, the exact shape and what shape it is, but that's quite complicated, and there's a lot of physics going on to determine what stars make what black holes. But one interesting piece that we can look at, though, is up at this top end, around 40, 45 solar masses, where there is seemingly a drop in the number of black holes, and this is what we call the pair instability mass gap, where we think that basically you stop making black holes above this limit until some later point where you can make black holes again. And the LIGO from the first 2 observing runs says this is about 43 plus or minus 10 solar masses. I'll talk a little bit at the end about the 03 data, what that says. So how does a star make a black hole, and why are we limited to 45 solar masses? So if you imagine a massive star, maybe a few hundred, of order 100 solar masses initially, it evolves, burns hydrogen, burns helium, and eventually ends up with a core of carbon and oxygen. As this core evolves, it gets hotter, it gets denser, and it can basically start producing electron-positron pairs in its star inside the core. This removes the pressure support from the star that was holding it up, so it contracts. The gas that contracts, it heats up. Eventually, at some point, it'll ignite oxygen, and then you get basically 3 different pathways. Either this oxygen ignition is kind of weak, and you'll get a shock, and this will drive a few tenths to a few solar masses of material from your star, and then your star contracts back again and does this cycle a few times, eventually making basically your 45 solar mass black holes. If this oxygen ignition is a lot more violent, though, you effectively only have 1 pulse and your star is completely disrupted as a pair instability supernovae. This is quite interesting because you'll make up to 30 solar masses of nickel 56, so there's lots of interesting nuclear synthesis here. And then if you have a much more massive star, this oxygen ignition is simply not energetic enough to unbind the star, and you'll collapse and make, say, 150 solar mass black holes. And because of this pair instability supernovae, leaving behind no black hole, this is why you get a gap. So you're making 40, 45 solar mass black holes. You stop making black holes because you're basically destroying the star before it can make a black hole. And then you'll start making black holes again at a much higher mass. So how does the carbon alpha rate fit into all this? Well, you can actually ignore a lot of this. Really, the carbon alpha rate is setting the star at this point. What does the core of the star look like as it enters this cycle? So which stars do which of these different processes depends basically on the mass of the core. And then to a second extent, it depends on the carbon to oxygen ratio. And the carbon to oxygen ratio is set at the end of core helium burning by this reaction rate. So how does changing the carbon to oxygen ratio change the end state of a star? Well, if we start with basically a star, so these are 3 stars with the same mass, so it's 60 solar masses in this case. If the reaction rate is very small, then you'll have a lot of carbon left over, right? You won't have burned it into oxygen. If the rate is kind of a median rate, right, at the values that we expect, you'll have some carbon, but not a lot of carbon left. And then if the rate was very high, then you've basically got no carbon in your star. You've turned it all to oxygen at the end of core helium burning. If you take the case with a very low rate, well, as you've got a lot of carbon, that will burn in carbon-carbon burning. If you've got enough carbon, you can basically start convection in the star, which mixes more fuel, which keeps the burning going. And this burning basically stabilizes the star and stops it going through this explosive process, and you end up with basically a very massive black hole at the end. When the rate is larger, you've got less carbon, so your carbon burning then becomes less energetic, it's less stabilizing to the star, so you'll undergo these pulsations which drive mass off the star, and you'll end up with basically a lower mass black hole. And then finally, when the rate is very high, you've basically got no carbon, so you don't even get a little bit of stabilization. You'll go straight through this explosive process and completely disrupt the star. So as the rate increases and you decrease the amount of carbon, you decrease the mass of the black hole you get at the end. So how does this, feed back to this 45 solar mass limit? So you can go and basically run the models, understand, what is the maximum black hole you can get out of a grid of models. So what I'm showing here, so this is the maximum black hole mass as a function of the sigma C12. So using the StarLib library, which is based on the Kunz et al. Rate. This is basically Gaussian sigma, so you've got a median, and then this is, plus minus 3 sigma variation in the rate. You can see that as the rate increases, the maximum black hole you can form decreases from about 100 down to 40 solar masses. On the right is the LIGO data, the individual events from the first 2 observing runs, and then this red region is basically the 90% confidence interval on what the maximum black hole mass could be or is expected to be. And from this, you can basically compare the red region to the curve, and this then effectively constrains what your rate should be. And it's about from basically minus 1 sigma all the way up. We can't quite get an upper limit yet because the LIGO data goes below the curve. So if we turn this into S factors rather than sigmas, so it's a bit more physical. So in green is basically our estimates from the 0102 data. So at 68% confidence, we're saying that the rate should be above about 170 kV barns, which is pretty consistent with where all the other lab measurements have been putting the rate over time. So that was with the 01 and 02 data. With the 03 data, things get more complicated, but that just means it's, there's more we can test with our theories. So originally we only really had objects up to about 40. Now we see objects above 40. In principle, this is difficult to explain because you don't expect stars to be making these black holes, but there are different possibilities. Maybe the reaction rate is very small and we end up on this end of the curve, but perhaps more likely is we've got other ways of making the black holes in the data, maybe multiple black hole mergers in AGN disks. There's lots of stellar physics that may be changing, whether you've got hydrogen on your star or not, but still there is a feature at 40 that might be the indication of the pulsational pair instability happening. I have to say that, the future's bright at this point, right? LIGO, we're currently in this 03A point where we've got about 40 objects. The next data release will probably double that. But in 10 years, we'll have hundreds, maybe even 1,000 binary black holes. So we're going to be able to do a lot better with our data as we get more black hole mergers. So I'm just going to leave the slide up for basically thoughts for the future. So the big thing is really going to be, can we understand the LIGO population, subpopulations, are there different formation channels? What do we think we need to still add to the stellar models? Binarity in a fully consistent way is a big thing. On the nuclear physics side, considering other reaction rates, started to look at that, but there's still more work to look at, especially things like correlations with rates. So triple alpha is a prime candidate, carbon-carbon, oxygen-oxygen burning. Also just looking at, updated reaction rates. Everyone always asks me what would happen if you used the de Boer rate. Well, you'll get a similar answer, you just change your uncertainty measure a little bit. And perhaps also to think about in the future, are there other features we can look for in stars? This pair instability edge is pretty useful because it should be quite a clear signal, but are there other signals we should be looking at, say white dwarfs, X-ray bursts, or core collapse supernova? Thank you.